description about thin film solar cell. As we all know, the conventional sources are no longer available in large quantities. It is prime time for us to think of new renewable methods and materials. So we know so many renewable energy sources like solar energy, wind energy, geothermal energy, etc. And common non-renewable sources are fossil fuel and nuclear energy. And out of these, I will be mainly focusing on solar energy, which is readily available for us every day. So now coming to solar energy, sun sends abundance of energy, and we can consider the sun as a huge fusion reactor, and that too working for more than 4 billion years. And all these years it worked free of cost, and even today also the energy is free. And it is estimated that the energy produced in a sun in a second is more than enough for everyone to use it for the whole year. And the energy it reaches the earth in 3 days is equal to the total energy we can get from all the fossil fuels present in our planet. But still we are not using it. Why? We are still depending on our traditional methods. The problem is not with the source actually, but it is with us, because we don't have the sophisticated technique for the conversion and storage of this whole energy. So the solar energy, we can divide it mainly into solar thermal and solar photovoltaics. So solar thermal is mainly used for cooking and heating purposes. That is, when we use a solar cooker, actually it is a solar thermal collector. What it does is it gathers and traps the sun's energy and use it for cooking. So we don't need any fuel for that. So no trees or habitat is lost. So there is no smoke, and that no smoke means no air pollution. And here the food is cooked very slowly and thoroughly, so that it is reported that almost 90% of the nutrients are preserved in it. And it totally eliminates all the fire dangers. Then coming to heating, solar heaters are usually installed in the rooftop with a collector facing the sun. So, and it is connected continuously to a water supply. So what will happen when the water flows through these pipes? It will absorb the sunlight and will become hot. And this hot water is stored in the tank for further use. Now coming to the second use of solar energy, that is the main use, which is in photovoltaics. But before we move more depth into it, we should recollect some of the terms that we require throughout this journey. That is, the first one, what is a photon? Then second one, what is photoelectric effect? And how this photoelectric effect is different from photovoltaic effect. So let's see one by one. So first is photon. What is a photon? Photon is an elementary particle, which is a quantum of electromagnetic radiation such as light and radio waves, etc. And these photons are massless, so it can travel at the speed of light in vacuum. Then comes the photoelectric effect. So it is found that when light falls on certain materials, the electrons are ejected out of their surface. So this is known as photoelectric effect. When light falls on it, electrons are ejected out of the material. Now, in the case of photovoltaic effect, what happens is that we know each material, there is a valence band and a conduction band. In photoelectric effect, what happens is that when light falls on it, the electrons present in the valence band absorb this energy and will jump into conduction band and become free to move inside the material. In the case of photovoltaic photoelectric effect, the electrons are knocked out of the material, whereas in the case of photovoltaic effect, the electrons are knocked out of their atomic orbitals, but they can move freely inside the material, not out of the material. That is the difference between two. And now, why the solar energy and devices? As we all know, solar energy is environment friendly and is renewable source. And solar devices, there is no moving parts. So, and it works very silently. So what we need, the maintenance cost and all other procedures will be very low for solar devices. Now, if we look back into history, we will see that even in 7th century BC, people figured out how to concentrate solar light and to make fires using magnifying glass. Later, in 1839, which marked a big year, when Edmund Becquerel discovered the photovoltaic effect. Later, in 1883, Charles Fitts came up with the plan of making a solar cell. And finally, in 1954, David Chaplin, Calvin Fuller, and Gerald Pearson of Bell Labs came up with or credited with the world's first solar cell. So still then immense research is going on in this field, and we can divide the photovoltaic devices mainly into three generations. That is the first generation crystalline solar cell, second generation thin film solar cell, and third generation high efficiency or novel idea solar cell. From now on, I will be mainly concentrating on the second generation, that is thin film solar cell. So with this, let me show you the video of how the conversion happens starting from the photons coming from the sunlight. So it reaches the earth and we have a solar panel. So what will happen, these photons will fall on the solar panel. As we know, solar panels are p-n junction. So when light falls on it, electron hole pairs are created. And when it is connected to an external circuit, we'll get the current. This is what happening in a solar cell. So now we know solar cell is an electrical device that converts light energy directly into electricity using photovoltaic effect. And we can integrate each solar cell together to form a solar photovoltaic panel. And almost 90% of world's photovoltaics depends on some or other variation of silicon. So we can say silicon as the king among photovoltaic materials. But the problems like requirement of bulk amount for its fabrication and expensive and complicated purification process and wastage of material during the processing, all this makes the silicon cell a little bad. And moreover, there are now reports suggest that the silicon cell has almost reached its theoretical efficiency. So almost most of the research are done on it, and so far it has achieved the theoretical efficiency. So we have to move on to some other methods, and so for that we have selected the thin films. So why thin film? Because as I have mentioned, the silicon wafer, in order to get a device, we have to do several operations which are very complicated. But in the case of thin films, all these are bundled into one process. And as the name suggests, we need only minimum amount of material. Thin film is minimum amount. So the material cost can be reduced. And also we can adopt so many easily deposition methods. So now let's see what is the structure of a thin film solar cell. Basically, a thin film solar cell will have a substrate over which we coat a transparent conducting oxide, then an absorber layer, then over that a buffer layer, and finally a metal contact. So here it shows the schematic diagram of a proper thin film material. This absorber layer can usually we'll call as a N-type layer, and a buffer layer usually we'll call as a P-type layer. So now coming to the function of various layers. So first one is absorber layer. So the performance of a thin film solar cell basically depends on the absorber layer, because it is in this layer the absorption of light and generation of carriers takes place. So for this we require a material with an optimum band gap of 1.2 electron volt to 1.5 electron volt, and the material should have high absorption coefficient. Then comes the buffer layer. The main function of this buffer layer is to form a junction with the absorber layer. So it should admit maximum light to the junction. At the same time, the recombination losses and the resistivity all should be less. And usually much more wide band gap material is selected for buffer layer. And finally, the transparent conducting oxide, which is the front contact of our device, and its function is to carry the current that is produced in the solar cell. So it should be transparent, and we should use a wider band gap, more than 3 electron volt band gap material should be used, and the sheet resistivity should be very low. Now, as I have shown the schematic diagram, so next question is how we are going to deposit each layer. And moreover, once we deposit each layer, how we are going to stack, as I have shown, the absorber layer, over that buffer layer, then the electrode and all. So for that we have various chemical routes and physical routes. And here I will be mainly focusing on physical route, which is spray pyrolysis technique. So this is an automated spray pyrolysis technique machine. So we have a substrate, heater substrate at the middle, and over that we'll keep our sample, and there is a spray head nozzle up, so that spray head can move in X and Y axis so that a coating can be done. And the precursor is filled in the precursor container outside, and that precursor solution is sprayed onto this substrate using air as the carrier gas. So in this way, we can coat large area films, and also the doping and multiple coating all are very simple in this method. So let's see how the film is forming in this spray pyrolysis. So that, as I have mentioned, first we'll spray the solution onto a heated substrate. So when the droplet falls on that substrate, what will happen? It will spread into a disc-shaped structure, and it will undergo thermal decomposition. So the size and shape of the disc depends on mainly on the momentum and the volume of the droplet, and also the substrate temperature. So the film what we get finally will be overlapping layer of these metal salts. So each layer, so in order, as I have said very easily, it is not that much easy. We have to optimize so many parameters to get a good quality film. So for each layer, first we have to find out the temperature, particular temperature at which we get a good film. Then the spray rate and all the precursor, molarity, viscosity, the concentration, all these things we have to optimize. Then only we will get a good film. And when we get a film, we have to do so many post-deposition techniques also. So once the film is prepared, we have to give inversion or annealing. Depending on the properties we require, we have to give post-deposition treatments also. So now the question, why we need an optimum temperature? So for each material, each layer we will be preparing it with each material. So each material, there will be a particular temperature at which we get a good quality film. So below and above that temperature, the material will have secondary phases which can affect the property of that material. Suppose if the temperature is very low, what will happen? The precursor will fall as a drop onto the substrate. That will give out a very bad film. And so on the other case, if the temperature is very high, this precursor will vaporize even before it reaches the substrate. So only the solid particles will fall on the substrate, and that will also result in very bad film. So we need to optimize the temperature first. Then comes the optimum spray rate. So spray rate is defined as the milliliters of precursor solution released per minute. So here also, if we need a film with a required thickness, suppose if the spray rate is very low, we have to deposit for a long time. So when we deposit for a long time, the heating will change and can affect the film properties. And if the spray rate is very high, what will happen? So much of solution is falling on to the substrate, so that the temperature of the substrate will decrease, and that can cause other problems in films like increase in surface roughness. And moreover, the deposition won't be proper because there won't be enough time for complete thermal decomposition before the next layer of coating. So we have to optimize the spray rate also. So similarly, we have to optimize the molarity and all the chemical composition before we spraying onto the substrate. So now we imagine we have optimized all the spray rate, substrate temperature, molarity and everything. And for each layer, we found out which is the correct temperature, spray rate, and for P layer, N layer. Now the next question is how we are going to stack one over the other. So for that, what we'll do, we use mask, Teflon mask. So we'll have a substrate, and we'll have a glass plate, and we can conducting layer. We can have ITOs or FTOs, and we'll mask the side where we need to take the connection. And over that sample, we'll spray the first layer. Then again, we'll mask the first layer, and over that, we'll spray the second layer. And finally, we will evaporate silver electrode is evaporated. So when we see, it looks so bulky, but actually the film is so thin that no, this is the film I have prepared like 2 years before. Till 1 year it was working. Now I am not sure whether it is stable. So it is so thin. It's not that much bulky, but all the processes are done in this small area. So the top view will be like this. So this is the round ones are the electrodes what we coat, and we can have two possible ways. Either we can coat the N layer first and then the P layer, or we can have P layer first and then the N layer. So that depending on our need and our properties required, we can change it. So each we can coat it in large area, so that in a cell we will get almost like 9 devices. So each electrode we will insulate, and at a time we will get 9 devices, so that it is easy to compare and establish our work. So now imagine we have prepared all the devices, all the layers are stacked, and we have a solid cell now. So now our next aim is to improve its efficiency. We will be having a small efficiency. So the next, once we have a cell, the next aim is to improve its efficiency. So for that, we can have different methods. Either we can change the architecture of this device, or we can add certain layers, like you can add one top layer above the N layer, or we can add one layer below the P layer as a blocking layer, or either we can add between N and P layer as a sandwich layer, or any ideas we can use. And then apart from that, we can I also change the properties of the existing layer. We can dop N layer, or we can dop P layer, or thickness we can change. So what all ideas we have, we can try on it, and in that way we can improve the efficiency. So now we have improved the efficiency and we get a final good cell. Now how we are going to know how this cell works, whether the cell we have prepared is perfect or not. So that is our next question. So for that we have to know how the cell works when it is illuminated. So we know this solar cell is a PN junction basically. So when light falls on it, what will happen? Electron hole pairs are created. So the three basic processes that happens here is, first is when light falls, the carrier generation, and the second one is carrier separation. At the junction, carrier separation will happen, and when we connect to the external load, we will get the carriers collected. So these are the three things happen. And so for that, how we'll know whether our device is perfect? So for that, we have mainly 4 output characteristics. So the first one is performance parameter. First one is short circuit current. We'll check the short circuit current of our device, then open circuit voltage of our device, then the fill factor, and finally the efficiency. So what is short circuit current? So short circuit current is actually the maximum current that we can get from a solar device. So this is a schematic diagram of a solar cell. So you can see that there is an external load resistance. So suppose that load resistance is 0. Imagine there is no load resistance. So what will happen? All the current will flow through that resistance instead of flowing through the diode. So the current when we get when the load resistance is 0 is called, that is the maximum current, and that is called the short circuit current. Then next case, open circuit voltage. So here we'll see that the load resistance there is high, it's open, that is the resistance is so high. So what will happen? No current will flow through the external load. Instead of that, all current will flow through the diode, and at the same time the potential across the load resistance will be so large. That is the maximum voltage that we can get from a solar device. So now coming to the fill factor. So fill factor is defined as the how much power we can get from a device. So it is also said that it is the measure of squareness of IV characteristics. So this is the current voltage is IV, and we have that Vm and Im is the voltage and current corresponding to the maximum power we get from a cell. So the fill factor says it is the squareness. So I'll show how it comes. Suppose if the fill factor is 25%, the IV curve will look like this. So the maximum power point will come as an area inside that. So that will give a small square. And now suppose the fill factor is like 50%. So the curve will be like this. So the area will be, the square will be more. And now if suppose the fill factor is like 100%, the area will be a perfect square and the power maximum will be there. So depending on the fill factor, it shows how much area we are getting in IV characteristics. That's why we say the fill factor gives the measure of squareness of IV characteristics. Then finally comes the efficiency. So efficiency, as we all know, it is the output power to input power, and we can calculate using the equation. So from the efficiency, we will know how much efficient is our device and how much perfect is the prepared sample. So whenever we make a device, we can't make it so perfect. There will be some resistance produced. So in the case of solar cell, there are mainly two types of resistance, that is series resistance and shunt resistance. So series resistance is mainly offered by the materials that we use for the fabrication. And since I have shown different layers, right? So in between each layer, there is some resistance. The interface resistance will be there. That will come as series resistance. And also when I evaporate electrode onto it, there is some resistance. That all will come under series resistance. If the series resistance is very high, the power will be low, and that will affect the efficiency of the solar cell. Similarly, next is shunt resistance. So what shunt resistance does is that it gives an alternate path. So we have a device like different layers. So the when shunt resistance come, it will give an easy path. Instead of going through the load resistance, it will give another easy path so that all the carriers will flow through it, so that we won't get any output. So that is shunt resistance. So for a proper cell, the series resistance should be 0 or minimum, and shunt resistance should be infinity or very high. Then only we will, if these two cases are there, only we will get a good output. Now suppose there is a doubt, what will happen if sun doesn't shine for long periods? If suppose there is a long period of cloudness, or when the days are shorter in winter, etc. So of course we need a backup power. So whenever we do research in thin films, we should always think of battery section also. These both will go together, so that when the research on battery is so important. We all are familiar with car batteries. So nowadays, because of research, we can say that almost like 100 times better capacity of car batteries are available. So even if the sun doesn't shine for one day, we can manage with that. So it is not a big problem right now. With this, I'll conclude my presentation. Thank you. That we have to do the, that's what in chemical spray pyrolysis, first we have to, if we have a material, we'll have some criteria, that is for absorber layer, the thickness and absorption coefficient should be this much we have. So we'll select a material. So once we select a material, we have to by trial and error method, we have to find out which thickness and which spray rate it gives the best values, like all the, so we'll separately, we have to first study the material, then we'll try stacking one over the other. Thickness profilometer, SEM also we can, for cell we can check in SEM. Thickness profiler for material we can study, use thickness profiler, or SEM for cell device. Okay. For taking the reading? Not for taking the reading, on a convent, not on a research basis. On a, if you commercialize it, for any even solar cell, it will work if the temperature is a particular temperature. Correct? If it is very high temperature. The efficiency will be low. Okay. What is it in case of thin films? For thin films, we usually, when we make a device, we'll try its stability and the temperature stability. So compared to silicon, nowadays there are silicon like gallium arsenide and all. It will withstand all the temperatures. I mean, the efficiency will remain same even if you go at higher temperature. That's why they use it for satellites and all the things. But with my material, what we do in lab scale, the temperature should be ambient only. If you increase, the efficiency will decrease, because the material property will change when we increase the temperature too high. Yeah.
How do you do the second layer? Do you mask it again? Or
Yeah, we'll mask it. Depending on the layers we need, we'll mask it. Because we'll have a large area. First, we'll mask for the output. Then for first layer, we'll keep some space. We'll mask it, and remaining portion we'll do the second layer. Then again we'll mask it. Remaining portion we'll do the third layer, and finally at the top we'll give the electrode. Depending on how much layer we need, we'll mask and we'll do. 21. Ah. Ah. Hmm. Purity of the precursor solution, oxidization happens. That for usually uh, there is oxygen presence in most of the film, and we'll when we spray it, we'll keep it in at a particular pressure that the oxygen content will take from the XPS, and we'll check which particular pressure and which particular temperature the oxygen presence will be low. But we cannot completely avoid the oxygen presence. There will be, of course, there will. But up to a level it won't. Maybe on large scale it will, but in research scale we have, even I have studied the variation of oxygen in the preparation samples. There is not much effect. But for that we need different. But inert spraying, I'm not sure how it will come properly. Inert, not sure. Sir. Because my work was actually on spray. We can try spin coating also, because spray it is, even in spin coating you will get only a very small area. In spray coating we can have very large area, and when we commercialize, what they ask is not the small, how much you got in a small. It's quite good to show if we got a big cell with a big efficiency. So mainly we used to focus on the chemical spray piles, but spin coating also you can try. My work was mainly on spray coating, so I selected.
what happens if you take the medium instead of air as what happens if you use some other medium? What will happen? Will the performance of your cells degrade or upgrade?
Basically, that air what we use is only for spraying. It doesn't matter about the deposition of the material. For the precursor to spray onto it, we are using the medium as air. Even if we use some other gases, it's quite costly, but I don't think it will affect the material properties. What we get in film is what the sprayed deposited sample only, So I don't think there will be much change.
According to my understanding, the light actually forms the PN junction. In this, the light is falling on the PN.
No. So basically, as I have shown, it's actually totally transparent. So we have a N layer here, which is little bit dark, and over that a P layer, which is almost transparent, and then a transparent conducting oxide, which is almost transparent. So when we illuminate, what will happen if we are giving N layer or absorber layer at the top? It is in the absorber layer where the electrons are generated. So this absorber layer will absorb. If you're having that as top, what will happen? The electrons will get generated and will move to that junction. The role of P layer is only to form a junction. So if we have a junction only, we'll get the output. Because only at a junction we could collect the carriers, right? So there is, if we are keeping P at top, the light will go through P and then reaches the N, and there again the carrier will created and we'll get the output. That I showed the device. So actually this solar cell is a diode, PN diode. Current source. Diode, I'm symbolizing the cell device as such. That is not because the solar cell is a PN junction. So instead of that, I can draw a sun also. I am just representing that device. And it is, we have two resistance, one series resistance and shunt resistance. That's what I have shown. This one, sir. No, that is here only, sir. This is the temperature. For each material, it will be different. So I was just showing if the temperature, suppose if for my material which I studied, it needs a temperature of 390 degrees Celsius. For that, if I reduce the temperature to 250, what will happen? The solution will fall as such. That's what I shown in first. Yeah, it will be different. For yes, electrons, yes, sir. Yes. Of course, sure. Because if the temperature is the main thing, in spray pyrolysis, temperature and spray rate is the main thing. If we didn't get the exact temperature, half of the electrons will be lost. We won't get the good efficiency. The particle and each material and each layer, it will be different. And when we make a fabrication of the whole device, again the temperature we have to, of course, we have to optimize.
You talked about the efficiency, right? And you talked about, I mean, if you rearrange the layers, the efficiency can be increased. You have a number for how much efficiency can be increased.
That is, if I say about myself, when I first fabricated, it was like 0.1% of efficiency. And then I have tried stacking different layers. So top layer and block layer increased my efficiency to like 1%. But the sandwich layer, it didn't work for me. So then I changed the thickness. So when I changed the thickness, when I increased the thickness of the buffer layer, I didn't get much improvement in efficiency. But when I changed the thickness of the absorber layer, I could reach almost like 4%. So in the case of thin films, it's almost like very good efficiency. So that way, first from what I got, I actually when I got a device, I modified the structure to increase the efficiency. So that's why I explained that. Thank you.
We will meet again next week. Mr. Shivra will be joining us. He will be doing a wonderful talk. The details will be shared with you as soon as possible. So, see you next week.